Assalamualaikum and hi. We are from group OKMG. We'll be going to explain our integrated design project, which is to design a reactor separator for nitric oxide production plant. So this is from reaction engineering 1 and separation process 2 subject. So before we start, let us introduce ourselves first. My name is Ahmad Kamal.
Hi, I'm Nadia.
My name is Mohamad Izmal Hakim bin Rosli.
Hi, I'm Nafisah.
Hi, I'm Hanisah.
So for the process overview, nitric oxide is produced through the catalytic oxidation of ammonia using platinum rhodium catalyst at high temperature. So you all can see the Khir reaction for NH3 plus 5O2 equal to 4NO plus 6H2O. But there is a challenge, which is the reaction is highly exothermic and produces unwanted byproducts, and which also affecting its purity. So right now there is two things that we have to focus on. First is the optimization, which is the reactor selection to improve our efficiency and maximizing the NO production. And second of all is the purification system, meaning the separation part to remove, optimizing the removal of the impurities to maintain the sustainability.
Let's start with the reaction process. In ammonia oxidation, the reaction mechanism as described by a paper by Kang in the year 2000 involves multiple steps. We focus on the first step, which requires the highest activation energy, making it the rate determining step. The side reaction, which directly forms NO2 without intermediary steps, is also considered. These mechanisms are crucial for simulating the process accurately.
This section covers the production capacity of our nitric oxide system. Nitric oxide is mainly used in nitric acid synthesis with a global production of 78 million tons in 2013. Medical grade nitric oxide, however, requires high purity and is produced in smaller quantities. A medium scale manufacturer in China produces about 2 to 78.8 tons annually. For our proposed plant, we aim for a smaller scale of 1,000 to 2,000 tons per year. With an hourly production rate of 114 to 228 kg per hour, our simulation ensures stable production within this range for efficiency and consistency.
For ammonia oxidation, a pet bed reactor is the ideal choice due to its high conversion rate per weight of catalyst and efficient contact between reactants and catalysts. According to Fogler 2011, PBRs are scalable, easy to construct, and cost-effective, making them suitable for large-scale production. In comparison, fluidized bed reactors offer good mass and heat transfer but come with higher operational costs, while CSTRs provide uniform temperature distribution but have lower conversion rates. Reactor sizing is equally important to the reaction. It can affect the nitric oxide selectivity. A smaller reactor with short residence time reduces unwanted byproducts like NO2, while a larger one may improve conversion but risk over-oxidation. Optimal reactor sizing ensures high space velocity, efficient heat dissipation, and maximized catalyst surface area to achieve the best performance.
Now, let's go over the key assumptions made for our reactor sizing. First, we assume an ideal reactor with axial flow and no radial variation. Second, we assume a pure inlet feed, meaning there are no contaminants that could affect the reaction. Next, we maintain isothermal and isobaric conditions, meaning that temperature and pressure remain constant throughout the process. We also assume a steady state condition, implying that there are no fluctuations in concentration, temperature, or flow rates over time. Lastly, the kinetic data used in our model come from literature sources that do not account for the presence of catalysts. On the right, Figure 1 shows our reactor process model, including the composition of reactants and product at different stages of the process.
Using the data from simulation, a Levin spill plot is created. The volume of the reactor is determined by calculating the area underneath the curve. By integrating the equation explaining the curve, we got 0.284 meter cube. The estimated reactor volume is within the expected range for industrial-scale ammonia oxidation. Several papers indicate that it typically ranges from 0.1 meter cube to several cubic meters depending on the production capacity.
This section covers the optimal reaction conditions and catalyst selection for NO production. On the left, we see that higher temperature increases NO production by overcoming the activation energy barrier and promoting ammonia oxidation. The optimal range is 850 to 950 degrees Celsius, as exceeding this can lead to uncontrolled reactions and higher energy costs. On the right, we highlight the PTRH containing 5 to 10% RH catalyst chosen for its durability under high temperature and minimal metal loss. This makes it both efficient and cost-effective, ensuring stable NO production.
Moving to the effect of pressure. At very low pressure, the reaction rate is high but it drops significantly around 2 atm. This could be due to catalyst surface saturation where excess adsorption blocks active sites. Additionally, according to Lichtalia's principle, increasing pressure shifts the equilibrium towards fewer gas molecules, potentially suppressing the forward reaction. Anyhow, for optimal conditions, maintaining pressure close to 1 atm ensures the highest reaction rate and efficiency.
Now, let's discuss the relationship between residence time and ammonia conversion. As shown in the graph, ammonia conversion increases with residence time because a longer duration allows more time for the reaction to occur. However, excessively long residence time have drawbacks. They reduce the reactor's output and increase operating costs, making the process less efficient. The optimal residence time is approximately 0.0005 hours, providing a balance between high conversion and efficiency. However, if the main priority is maximizing ammonia conversion, a longer residence time may be preferable, but this comes at the cost of reduced throughput and higher operational expenses.
So now we can discuss on impurities, identification and consideration of inherent impurities from ammonia oxidation. So the main reaction of this, the whole reaction is the catalytic oxidation of ammonia. The reaction is carried out using platinum rhodium catalyst under interesting condition of 800 to 900 degrees Celsius and 50 to 10 bar, while the primary product are nitric acid and water vapor. Such reaction lead to the formation of nitric impurities. Unreacted ammonia, despite optical condition incomplete, combustion due to kinetic limitation result in unreacted ammonia. The concentration of NH3 in the feed is typically around 5 to 10%. If not managed, excess ammonia can interfere with downstream processing. Nitrogen dioxide. Nitrogen dioxide formed as a secondary product due to the partial oxidation of nitric oxide. The concentration of NO2 in the product stream is usually around 2 until 5%. The presence of NO2 is influenced by oxygen availability and residence time. Water vapor. Water vapor is another major product of the main reaction, constituting around 15 to 20% of the output from the main reactor. While it condensed during the cooling, its removal is essential to prevent interference with downstream adsorption process. Nitrous oxide, N2O, a minor but significant byproduct is nitrous oxide, which forms due to intermediate cell reaction occurring at subthermal temperature. The concentration of N2O is typically around 0.5 to 1%. This impurity is particularly important in environmental consideration due to its role as a greenhouse gas. Lastly, excess oxygen. Excess oxygen remains in the system from the air feed. With air conditioning 21% O2, the unreacted fraction typically makes up about 2 to 5% of the product stream. This depends on the cinematic and operation condition. Lastly, the factors affecting political concentration. Several factors influence impurity levels. Available temperature 800 to 900 degrees Celsius favor NO formation over N2 and N2O. Excess oxygen enhances NO2 production through secondary oxidation. Longer resistance time reduce NH3 presence by may increase NO2 formation due to extended NO exposure to oxygen. So now we're gonna discuss on design purification system to purify nitric oxide. So firstly, the process begins with two separate feed streams, which is ammonia and oxygen. Ammonia is introduced through the line NH3 feed line, while oxygen comes from O2 feed line. These streams are mixed at S1 to form a homogeneous reactant stream. Next, the stream is directed to a heater, H1, where it is preheated to around 750 degrees Celsius. This high temperature is essential for initiating the catalytic reaction in the next stage. After heating the stream, the stream enter a plug flow reactor, PF1. Here, ammonia reacts with oxygen over a platinum rhodium catalyst to form nitric oxide and a water vapor. This step is critical for converting ammonia efficiently. Once the reaction is complete, the hot gas mixture exits the reactor and is cooled in a heat exchanger, C1. Cooling is necessary to prevent unwanted side reaction and to prepare gas for separation. The cool gases move to separation unit as CSP1, where unreacted ammonia is removed and recycled back into the process. The remaining gases enter another unit, ADS1, which purify the nitric oxide stream to 99% purity. The process introduces two output streams, a high purity nitric oxide stream, which is called for the use, and nitrogen dioxide byproduct stream. Unreacted ammonia is recycled back to the feed to maximize efficiency and minimize waste.
For the type of adsorbent used, we use activated carbon MAC6D40CZ for the NO removal. The adsorbent properties is as follows. The mass is 76 gram, the particle diameter is 2 to 2.8 millimeter, the density is 0.73 gram over centimeter cubic, micropore radius 0.91 nanometer. So the column type and configuration, we use a fixed back column Okay, so for the experimental assumptions, since we use experimental to develop a to develop an industrial design, so this is the experimental assumptions. Okay, this is the experimental breakthrough curves of NO and on activated carbon. I found it on research paper that's ranging from 0.28 mole percent to 1 mole percent. This is very crucial in our calculation because we want to know the breakthrough time. So then we develop an absorption isotope model using that absorption capacity of activated carbon, which I found it on also in the research papers. Okay, so we plot the graph Langway and Franklin isotherm graph, and we found out that Langway is provide better fit than Friendlich. So we can conclude that the isotherm model for this process is Langway isotherm. So this is assumptions for industrial application. Scale up design method, which assume HUMB is constant with the total of the bed length. Adsorbent properties remain the same as I mentioned in the first slide. And absorption kinetics follow a consistent mass transfer behavior. As for the calculation assumptions, the total bed length is scaled up to 5 meters, since the absorption column in the industrial ranging from 4 to 8, so we choose 5 meters. And the mole composition of NO ranges from 0.28 to 0.8 mole percent, because that's the only data that I know from the research paper. So from the graph, for graph 5, we can determine the breakthrough time and saturation time at the respective mole composition. Using the provided data, the MTZ, breakthrough time, and the bed utilization can be obtained as below. So the table provided all the data that I included after I do the calculation. For the absorption system design, the best choice is 0.8 mole percent based on the calculation, but the actual process produced only 0.28 mole percent NO, depending this 0.28 mole percent from the symmetry at the reaction engineering part. So this is the data that is from 0.28 mole percent NO absorption. So this is aligning design of actual NO concentration, ensures efficiency and minimal waste. So for the desorption and regeneration, I use pressure swing method. Regeneration via PS, using the adsorption at high pressure, depressurization to dissolve NO, purging with inert gas, maybe NO, repressurization for next cycle for the activated carbon to absorb more NO. I think that's all for my part. Thank you.
In conclusion, for reactor design and production, ammonia oxidation follows first order kinetics. Packed bed reactor, PBR, is selected for the reactor. Temperature optimized at 850 to 900 degrees Celsius at 1 atm. Volume for the reactor is 0.284 meter cube. And for purification part, the key impurities detected is NH3, NO2, and H2O. Langway isotherm is chosen, and best condition is 0.8 mole percentage of nitric oxide, and multi-stage adsorption ensures continuous purification. So overall, optimization, we managed to maximize the nitric oxide yield and minimize the byproduct, thus enhance our purity. And also, this integrated design project ensures the efficiency, scalability, and the sustainability of the reaction.